I was in high school, the most fascinating chemistry experiment to me was titration. I still remember so vividly the first time I stood in the lab coat on, adding the base to the acid in a flask, one drop at a time. Then suddenly, there was a change from colorless to a perfect pale pink. In chemistry, we call that the end point. It's the moment of perfect neutralization. Years later, I realized that we are in desperate search of a new endpoint in medicine. Our antibiotics are failing, the reactions is spinning out of control, and there is a need for alternative treatment strategies. Scientists are searching for answers. This answer can be found in a biological precision tool, a virus that finds its target bacteria with the exact precision I was hunting for in high school. Antibiotic resistance is a global health challenge. It is caused by the misuse and overuse of antibiotics. Each year, it results in approximately 5 million deaths worldwide. In the US alone, more than 2.8 million antibiotic-resistant infections occur annually, resulting in over 35,000 deaths. Antibiotic resistance is projected to cause 10 million deaths by 2050. Bacteriophage is also known as phage, and it is a virus that infects bacteria. It's able to infect its bacterial targets so specifically, and they do not infect human cells. Because of these characteristics, they are being employed in the treatment of bacterial infection. This is known as phage therapy. Imagine bacteria as a building with a giant door and a key knob. Antibiotics are the keys that fit into the key knob and are able to unlock the door. Most bacteria have been able to develop antibiotic resistance by slightly changing the key knob, which makes it difficult for the door to be unlocked. Phages, on the other hand, are able to bypass the key knob and unlock the door. The phage can then target the bacteria alone or in combination with the antibiotics, which leads to the killing of the bacteria that causes the multidrug resistant infection. In 2016, Tom Patterson was cured of antibiotic resistance using phage therapy. The doctors had no choice because they had exhausted every other treatment alternative, and he was in a coma. After several months of research, 4 phages were made into a cocktail and administered to him. Slowly, Tom recovered, and the infection cleared. The phages that were used to successfully treat Tom were all wild-type phages, and they were gotten from environmental samples. These wild-type phages have several limitations, one of which is limited host range, and that is where my research comes in. My research is focused on engineering the phage by modifying the tail fiber that binds to the bacterial receptor. We've been able to establish the fact that the tail fiber of the phage can be modified. By growing the phage, which is being engineered with the antibiotic-resistant bacterial strain, we are able to isolate the phage of interest. It's like training the phage with the bacterial defense system. Think of it as an evolutionary trap. To dodge the phage attack, the bacteria is forced to drop down its shields. It's a win-win for us. Either the phage directly destroys the bacteria, or it leaves the door wide open for the bacteria to finish the fight. The patient heals and the medicine works. This is the future of phage therapy.